Hello everyone. In last video we have discussed about the irradiation, which is simply the energy that is coming towards a surface or incident on a surface. In this video we will be talking about the energy that is going away or which is get emitted from the surface, which is known as emissive power. We know that all bodies at a temperature above 0 Kelvin will be emitting energy, and that energy emitted will be measured by a quantity known as emissive power, represented by capital E. The emissive power is defined as the total amount of heat energy emitted by the surface in all directions over the entire wavelength per unit area per unit time. So amount of energy is joules, per unit time makes it watts, per unit area makes it watts per meter square. And we have mentioned that what a black body is in the last video. It is a body which is absorbing all the radiations which is falling. That means absorptivity alpha equal to 1 for a black body. So if you are considering a black body, the emissive power of black body will be represented by capital E suffix B. And we know that this radiation energy is depending upon wavelength and directions. And last video itself we have mentioned that the irradiation, that means incident energy or this emitted energy, emissive power, can be expressed for a particular wavelength. So if you are specifying for a particular wavelength, then it will be becoming spectral or monochromatic. So similar to this emissive power, you can define spectral or monochromatic emissive power. This is simply the amount of energy emitted by surface at absolute temperature T per unit time per unit area extra per unit wavelength is coming. So it will be represented by E suffix lambda, and its units will be watts per meter square and extra micrometer. So this spectral or monochromatic emissive power will be becoming dE by d lambda. So you can find the total or simply the emissive power as the integral over entire wavelength range 0 to infinity. E lambda d lambda will be giving you the total emissive power from the monochromatic or spectral emissive power. The monochromatic emissive power of a black body can be written as capital E B suffix lambda. Next we will be seeing what is radiation intensity capital I. I have mentioned that the radiation emitted is depending upon wavelength and direction. So per unit wavelength you can represent it by monochromatic or spectral term. Next we will be looking for what is the energy emitted in a particular direction, or we will be looking for the directional distribution of the emitted energy. And this directional distribution can be given based on a quantity in which is known as solid angle. This you have studied in your +2. Solid angle will be represented by dW, whose unit is actually steradian. So we will be seeing what is a solid angle. This is actually a 3D angle. First we will be looking for the symbol 2D angle. 2D angle is the angle which is made by this point on rotating about this reference point will be known as 2D angle theta, that which usually come across. Next we will be seeing a what is solid angle. For considering the solid angle, you can see this is a cone. So cone is pointed, this vertex is coming or apex point is coming here, and it is having a base here. So there will be a base area for this cone, and I will be drawing that base area here, and this is pointed towards this point, and we will be defining the solid angle. Solid angle is defined in such a way that this area will be calling it as dA, and if this dA is coming as a part of some hemisphere, if this dA is coming as a part of this hemisphere with this is the point, this is actually a hemisphere, and this will be the center, then this included angle made by this surface area dA about this point, that is this included angle, will be giving you the solid angle, which we will be calling it as dW. Means if you are having a cone here, and what is the included angle, that is this included angle will be giving you the solid angle dW. And this solid angle can be measured by, solid angle is defined as this area which is coming as a part of a sphere or hemispherical area dA divided by this, and this sphere will be having a center. At the same point the end of the cone is also lying. If this distance is r, or the radius of the sphere is r, then solid angle will be defined by this dA divided by r square will be giving you the solid angle. It is measured in units called, unit will be steradian. This you have studied and will be represented by SR. So this will be the unit steradian for the solid angle. So with respect to the solid angle, we will be measuring the radiation intensity. So if you are having an emissive power, you can measure radiation intensity. Radiation intensity is represented by capital I. So if you are considering a black body, it will be becoming I suffix B. For the analysis, you will be taking black body. So for which you will be defining this radiation density. So it is the radiation emitted by black body at a temperature over entire wavelength. Over for this intensity or for a directional distribution, we will be taking the projected area. Per unit projected area, per unit solid angle will be the radiation density. So I can write IB equal to energy emitted by projected area by solid angle. So units will be energy emitted watts, projected area meter square, and solid angle will be steradian. Earlier the emissive power is energy emitted divided by symbol area. So here it is projected area that you have to note. And here you can see an area dA, which is actually the surface which is emitting a part of black body, say. So this is dA, and here you have to find the radiation intensity in this direction, or radiation which is falling onto this area. So this area is coming at angles which can be measured in two ways, with respect to this vertical and with respect to this horizontal. So with respect to vertical or normal, this vertical is actually a normal to this dA at angle theta, and this variation over this element will be becoming d theta in this direction. And again I can project the element onto this sphere in this direction, and that element is lying at an angle phi with respect to this direction, and that element is projected over a d phi angle in this direction. So you can locate this element with respect to theta and phi. D theta and d phi are the angles over this element, and the included angle for this area, this is coming as a part of hemisphere. This hemisphere is the formed by the this radiations from this area dA will be propagated in all directions. At any time this will be intercepted by a hemisphere, and this green area is representing part of this hemisphere. So you can construct or consider a solid angle which is made by this area coming as a part of hemisphere, forming a cone at the center which is same as the center of a hemisphere. So you can find the solid angle, and I will be representing it by dW here. So radiation intensity is simply the directional distribution of energy emitted, and this is having a definition here. And again this radiation intensity can be defined for a particular wavelength also, which will be known as spectral or monochromatic radiation intensity, represented by IB lambda if you are considering a black body. And this IB lambda equal to energy emitted divided by projected area per unit solid angle, and per wavelength will be coming, whose unit will be watts per meter square, micrometer steradian. And if you are knowing the spectral radiation intensity, you can find the total radiation intensity over entire wavelength range by integrating 0 to infinity IB lambda d lambda. This is similar to the total emissive power and monochromatic emissive power. Here you are getting total radiation intensity from monochromatic or spectral radiation intensity. Next we have a law which is known as Lambert's cosine law for this radiation. Here you are having a surface which is radiating energy shown by this red surface having a area dA, and it is having a normal in this direction, and along that direction suppose it is radiating energy, total energy, it is not per unit area, it is total energy dQn. Next you are considering some other area which is shown by this green, located at an angle theta, and the amount of energy emitted in this direction I am writing it as dq suffix theta. And according to Lambert's cosine law, it states that a diffuse surface is actually a surface whose radiation properties are independent of directions. We have seen in the previous video that for a diffusion surface, the reflected radiations will be going equally in all directions. Means simply diffuse surface is one whose radiation properties are independent of direction. So for such a diffuse surface radiates energy in such a manner that rate of energy radiating in any particular direction is proportional to cosine of the angle between that direction under consideration and normal to the surface. Here dqn is the energy emitted in normal direction, and if you are considering another direction at a theta angle, energy emitted is dq theta. Then according to Lambert's cosine law, this energy emitted in theta direction will be directly proportional to cosine of this angle between those two, normal and the considering direction. Then you can write dq theta equal to dq in normal into cos theta. This is according to Lambert cosine law, based on which we will be taking some analysis we will be doing. Here we will be proving that for surfaces, diffuse surfaces which are obeying the Lambert cosine law, we will be proving that the radiation intensities are also independent of direction. For which I am defining the radiation intensity for this black body IB in a particular direction theta I am writing. We know that radiation intensity is energy emitted per projected area per solid angle, which is equal to theta direction I am taking. So it is dqb theta. Projected area is here the area dA whose normal is in this direction. If I am taking a direction at an angle theta, then this projected area in this direction will be dA cos theta. So projected area here it will be becoming dA cos theta into solid angle I am writing it as dW, and here it is same dq b theta by dA into 1 by cos theta into dW coming in denominator. Here I am having Lambert's cosine law, which is giving the radiation energy emitted in any direction is proportional to cosine. So I am writing dqb theta as dqbn into cos theta. Here cos theta will be getting cancelled. Then you are having dqbn divided by dA into dW. Here you can write this as, you can consider this as, if here normal direction is coming, for the normal direction projected area is dA itself. So it is like energy emitted divided by projected area in normal direction I am taking. So it is simply dA. That's why here dA you are having into solid angle dW it is coming. It is actually the energy emitted in normal direction. So energy emitted by projected area per solid angle is giving you the radiation intensity. In which direction? Normal direction. So you are getting, initially you took the energy radiation intensity in theta direction, and finally you are getting radiation intensity in normal direction, which means whichever directions you are taking at any angle, the radiation intensity will be same, or you can write it as simply I, or if you are considering a black body it can be written as IB. So it is a constant. That means for diffuse surfaces which obey Lambert's cosine law, they have a radiation intensities which are independent of direction, and such surfaces will be known as Lambertonian surfaces. So that's all from this result. Next we will be deriving a relation between the emissive power and radiation intensity for diffuse surfaces. The relation between emissive power and radiation intensity will be derived here. So here you can consider an elemental area dA which is radiating, whose normal direction is this direction. At any time the radiated energy, emitting energy, will be flowing in or moving in the in a hemispherical manner. So at any time the radiation will be intercepted by this hemisphere. You can see in this figure, this is the hemisphere that is formed. Now you are looking for the amount of energy that is falling or emitted in a particular direction. So you are taking some of the area that is, or element which is coming on the hemisphere in this direction. This direction is lying at an angle theta with respect to this normal, and for over that element d theta angle is there, and with respect to this horizontal direction, this element whose projections, if I am constructing over this spherical surface, then this element will be lying along this lines, and this is lying at an angle phi from the horizontal, and over the element there is an angle of d phi is there. So this is phi and d phi, and this is theta and d theta, and this is a sphere which is having a radius. The radius of the sphere is at r. Here I am rewriting or redrawing the element. This is the element which is having, this is the center of the sphere where our element is placed, which is having area dA. This itself is representing the distance up to this element on the spherical surface, which is actually radius of the sphere. And this angle is d phi. Hope you can see the pencil lines. These are representing the constructions, and this is actually our elements. We will be joining this to the center of the sphere to form the solid angle. The angle formed in between will be giving you the solid angle. Here I have redrawn all this, and here you can see the angles. This is d phi, and this angle 2D angle will be d theta. Here also I am showing. So if this is r, if this is r and this is angle is theta, then you will be getting this distance as r sin theta. You will be getting, this is, sorry, not this direction, this length, this length you will be getting r sin theta you will be getting. So for this element I have to obtain the solid angle. Solid angle is obtained by the area over the spherical surface divided by radius square. So I have to obtain this area. This area of this element I have to obtain, for which I will be requiring the dimensions of this side and this side. So if it is r and this angle is d theta, then this side will be getting r into d theta will be this side. And now this length is r sin theta. This angle is d phi. So this angle will also be d phi. So this is actually arc length. So it is radius, it is included angle. So you can obtain this side as r sin theta into d phi. So you are having the element whose area is r sin theta d phi into r d theta divided by r square. Then you will be getting solid angle for this element as sin theta d theta into d phi you will be getting. So I will be making use of this solid angle obtained for deriving the relation between emissive power and intensity. We know that intensity, here I am writing IB only because previously we have shown that the radiation intensity for a diffuse surface, here all these relations will be applicable for a diffuse surface, is independent of direction. So I can simply write IB, which is defined as energy emitted per projected area per solid angle. So energy emitted is dQB divided by projected area is dA cos theta. So solid angle is dW. Here I am having dW as sin theta into d theta into d phi I am having. So here this dQB by dA, which is energy emitted per unit area, I can write it as emissive power. dEB divided by cos theta into, instead of dW I will be writing this expression, then you will be getting sin theta cos theta into d theta d phi. Here I can write dEB equal to IB into sin theta cos theta d theta d phi. So I can obtain the total emissive power EB by integrating. Here we are having, here you have to do multiple integration over for both d theta and d phi. So you have to obtain the range of theta and d theta and d phi from this diagram. Here theta is the angle measured from the vertical. So this element can move from this vertical 0 to this line. That means theta will be varying from 0 to 90 degree or 0 to pi. Next, phi is the angle measured from this line. So it will be moving, and it can move along the complete base of the sphere. So it can move from 0 to 180 degree or 2 pi. So you will be applying this limit for integration. So it is theta equal to 0 to pi by 2 and phi equal to 0 to 2 pi, IB sin theta cos theta d phi, and upon integration you will be getting, finally this total emissive power EB will be equal to pi into IB. So this is a result for a diffuse surface. The total emissive power is equal to pi times the radiation intensity. This is a result for this diffuse surfaces, which is a black body here I am considering. So that's all for this video. Thank you.